All right, we got the light on. We're good to go here. Let's take a look at a special type of problem that the author discusses in section 4.5. And this is we can go into quite a bit of detail just on this one concept. So that's why I wanted to make this its own little video to discuss. And what we want to do is we want to see how do we model a free falling object. All right, we are going to consider this as three possible cases, each one building in complexity and actually handling the modeling process a little more sophisticated. Okay, first case we'll consider a very primitive case. We consider an object falling with no air resistance, meaning there's no drag. Think of this as you're dropping an object in a vacuum and you want to model how the object falls. Okay? Well, what governs all of this really is force is mass times acceleration. F equals ma from Isaac Newton. Okay? And so we consider our mass times our acceleration, which is the change in velocity with respect to time, not being impeded in any way, just being affected by gravity. No air resistance, just gravity acting on this. Okay? The force on your object, the mass times the acceleration, is the force on the object, where the force on the object is simply that of the force of gravity, no force due to air resistance in the problem. Okay? And so this may be a little bit of an artificial case to consider, but it's a good first step in learning about this. Okay? Now, of course, the very first thing we see is, if this is the case, then you can divide both sides by m, and your differential equation is very simple. dv dt equals g, which means you can separate the variables. Integrate both sides, and you get that the velocity of your object falling is simply gt plus a constant. Okay? Now, if we impose an initial condition on this free-falling object, suppose that we're dropping the object as we're holding it up in the air. We're just dropping it. So it's dropping with an initial velocity of 0. The velocity at time 0 is 0. When we plug that in, 0 for v and 0 for t, c necessarily will have to be 0 as well. So the solution we get is that this is how your velocity is modeled for the free-falling object. It's simply the force of effective gravity, 9.8 meters per second squared, times the time, how many seconds the object is falling, which simply says that this is an object that is going faster and faster and faster and faster as it drops, always accelerating as it drops. Okay? So the velocity is growing in this constant fashion with this rate of change, g. Okay? All right, so that's a bit artificial, because you realize when you drop an object in air, there is some resistance from the air that's going to cause that object to not drop as fast as this model would indicate. Okay? So let's consider that second case. This is an object dropping with air resistance. So there is drag on the object as it's falling. Okay? And in this one, we model the resistance, the air, is proportional to the velocity. All right? So as the velocity increases, the air resistance, force of air resistance increases as well in a linear fashion according to this. Okay? So the differential equation we would get for this, m times dv dt, that again is mass times acceleration, is equal to the force of gravity on your mass being impeded by some constant of proportionality times the velocity. In other words, as your velocity increases, the resistance is proportional to it by this constant of proportionality. Okay? All right. So this is the differential equation for us to consider. Now, the interesting thing about this, and the reason that's talked about in the context of section 4.5, is this is a first-order linear differential equation to consider. So I can rewrite this, dividing everything by m to get the coefficient on the dv dt to be 1, and then adding the kv divided by m to both sides. Again, dividing by m gives you g on the right. There's our standard form for this first-order linear differential equation. And now that I'm in my standard form, I can use my technique of the integrating factor to solve this. So the integrating factor is e to the power of k over m integrated with respect to t. So that's e to the k over m times t as our integrating factor. And we know by doing all those examples from section 4.5 already that you take the integrating factor times the v, and that's what you differentiate on the left-hand side to reproduce the equation on the left-hand side that has been multiplied by the integrating factor. And so on the right you have the equation multiplied by the integrating factor as well. All right. So now, let's see what we can do here. I can integrate both sides, right? On the left, e to the k over mt times v. On the right, I'm integrating this. In order to integrate this exponential, I'm going to need the derivative out in front, a k over m out in front. So I do that by putting an m over k to balance that. And now when I integrate that, I get just e to the k over mt plus a constant of integration. Okay? All right. Now, get v by its... let's apply the initial condition. Again, we're dropping the object with no initial velocity. So velocity at time 0 is 0. So you're putting in 0 for t and 0 for v, that's a 0. You're putting in 0 for t, that's going to be a g m over k times e to the 0, which is 1, plus a c. So that tells you that this constant of integration is negative gm over k. So let's put that in here. E to the k over mt times v is g over mk e to the k over mt plus this negative g over mk. Okay. Now, to get v by itself, I have to divide by this. As I divide by this, it's going to cancel here, it's going to cancel here, and it's going to be e to the negative km over mt here. So you're going to get g m over k minus g m over k e to the negative k over mt. And you've solved here for v. Okay? So now let's do the similar type of analysis that we did up here, where I said what happens as time goes on. Well, as time goes on here, right, your velocity grows and grows and grows infinitely. As t goes to infinity, the velocity goes to infinity. You just keep getting faster, 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 faster at this rate. Okay? But what happens here? As t goes to infinity, well, as t goes to infinity, what does velocity become? Well, this has nothing to do with t, but this does. As t gets infinitely large here, you get e to the negative infinity, which goes to 0. This term gets driven to 0 as t goes to infinity, because it's a decreasing exponential. And you're simply left with this right here. V approaches gm over k. So what this model is telling us is that for the object falling with air resistance, where we model air resistance to be proportional to the velocity, meaning if the the velocity doubles, the air resistance force doubles. Okay, then you're going to have a terminal velocity to your object, and the fastest that object can fall is according to gravity times the mass divided by this constant of proportionality that you used in the modeling of the air resistance, which is going to be a factor of whatever the body is that's falling. It's its drag, in effect, being calculated into that constant, okay? But that's going to be your terminal velocity, as opposed to having an infinite velocity that you're approaching. And that certainly seems more reasonable, right? You know, for example, if you were to jump out of an airplane, as a parachutist, hopefully, that you would have a terminal velocity. You would not just keep going faster and faster till you get infinite velocity, or until you hit the earth, right? You reach a terminal velocity, and you don't start falling faster and faster, okay? All right, now, the interesting thing about this is that while this was a nice and reasonable assumption to make, that air resistance is proportional to the velocity, it's not actually accurate, okay? Air resistance is actually proportional to the square of the velocity, not to the velocity, which means this was a simplification that we did simply so that we could make this a first-order linear differential equation. If we had done this correctly, there would be a squared on this velocity, and this would not be a first-order linear differential equation. Now, that's going to be the third case that we want to consider. I want to consider a differential equation that's first order but not linear. And what that means is we will not be able to use an integrating factor to help us. So while this was a nice theory that we learned in section 4.5, you have to remember it only works for first order linear differential equations. And so if you have something that's not linear, like a square on your velocity, the integrating factor does you no good. So it may benefit us to think, could I have done this case here, this case 2, where we're proportional to the velocity, this first order linear, could I have done it without an integrating factor? Maybe that's interesting to consider, okay? So let's revisit. Without using the integrating factor. Okay. So again, the differential equation that we're considering, m dv dt, is mass times gravity minus this constant of proportionality times your velocity impeding your fall, okay? And the question is, how in the heck would we solve this if I could not use an integrating factor? Well, you would simply separate the variables. All right, you've got the dt here that you're going to bring up to the right. This mg minus kv, you're going to bring that down underneath here. And so you're going to get the integral of m over mg minus kv with respect to v is equal to, all this is moved, right? So all that's going to be up here is this dt coming up. And you have separated the variables. Okay, that's the technique we learned prior to the integrating factor. Okay, you integrate both sides of that and you're in business. So how do we integrate this thing right here? Simple U substitution. You're going to let u equal this denominator. M and g are constants, k is a constant, v is your variable. Okay, differentiate u with respect to v. You get negative k. So solve for dv, because that's what you're going to have to replace here in terms of du. dv is going to be du over negative k. So coming over here, mg minus kv is your u. Your dv is du over negative k. And now we're all set to integrate this thing, I believe. Right? Take the m and the negative k out in front. And this looks pretty simple, I think. All right, let's go ahead and plug back in what u is, mg minus kv. All right, let's go ahead and multiply both sides by negative k over m to get rid of this coefficient. Negative k over m times a constant is still just a constant, so I'll call this C1 just to explicitly distinguish it from the original constant here. All right, now if I exponentiated both sides here, you know this constant can come down in front. All right. So, how would I solve this for v? I would subtract mg from both sides. Then I would divide both sides by the negative k. That's just going to be a constant divided by k. Which is yet another constant, right? Call that C2. All right, now let's apply the initial condition, figure out what this constant is. Velocity at time 0, again, was 0. So 0 here is mg over k plus that constant times e to the 0. That's 1. That C2 is negative mg over k. So the solution we get is your velocity is mg over k minus mg over k e to the negative k m times t. This is the same solution that we arrived at before. Mg over k e to the k mt. Right, okay, right here. Okay, and mg over k are there. And so the analysis you do, again, as t goes to infinity, your velocity, this goes to 0, is going to approach mg over k, your limiting velocity as the object falls. Okay? All right, so that was kind of interesting that we have actually two ways that we've learned how to solve that, right? First by the integrating factor, then simply by separation of variables. Now here's the interesting thing. When we go on to case 3 of this problem, case 3, air resistance is proportional to the square of the velocity of the falling object, which is the accurate model for this, actually. And if you've ever done any kind of sports that involved higher speeds, maybe higher than a slow run, you'd realize that this is true, right? Even if you're fast running or more cycling or automobile or motorcycle sports, you realize that in order to increase your speed once you're already going fast is tremendously difficult, because the air resistance you're encountering is growing in a squared fashion, not a linear fashion. And so that's what makes all of these speed sports so dependent on the idea of drafting off of others in the sport. Okay? If these were linear, drafting would not nearly be as important, but when you're running very fast, or cycling fast, or motorcycle or automobile racing, drafting makes a huge difference in the amount of energy that's expended to achieve a certain velocity. And it's because of this fact. All right, now let's take a look at how this plays out. Okay. We've got, let's see, m times the acceleration, the change in velocity, is mg minus the constant of proportionality times velocity squared. Okay? Now, this again is first order, but it's certainly not linear anymore. So I don't have the option of an integrating factor to solve this. I am stuck with having to do separation of variables. So this is going to come down into the denominator. And this dt, I'm going to move that up on the right-hand side. Okay? And that means now, once the variables are separated, I'm allowed to express the solution as an integral of these. Now, how am I going to integrate this? Well, I'm going to use partial fraction decomposition. Okay? The partial fraction decomposition that we have to do here is a little bit messy because, as you can imagine, factoring this quadratic term in the denominator is a little bit messy. So I have to take that m over mg minus kv squared and view it in a factored form. Okay, the factored form for the denominator is going to be the square root of mg minus the square root of k times v, and the square root of mg plus the square root of k times v. In other words, your linear factors are square root of mg minus square root of kv and the square root of mg plus the square root of kv. Which means when you multiply by the common denominator that you get m is this constant times this denominator plus b times this denominator. Let v be anything you want. So how about we let v be the negative square root of mg over k? Plugging that in for v, the square root of k's are going to cancel. You'll get negative root mg plus root mg. Those cancel. This term drops off. Over here, same cancellation, but now this is going to be a plus, so you're going to get 2 root mg. On the left-hand side, you get m. On the right, this canceled, you get 2b. Right? Times the square root of mg. So that means that b is this m divided by 2 root mg. When you let v be the positive square root of mg over k, very similar thing happens. The left-hand side is still m. These now will cancel, so the b term disappears. Over here, this will be root mg plus root mg. So here, a is m over 2 root mg. They're both the same coefficient. Okay? All right, now plugging those in for a and for b and integrating on the left-hand side. There's your a over the root mg minus root k v. On the second one, it's root mg plus root k v. And on the right-hand side, you integrate at dt. you got t plus a constant. Okay? All right, let's factor out the numerator here, which is common to both of these. And let's integrate these things with a simple U substitution. And what you will get is, let's see, the derivative of this is a root k, a negative root k, and the derivative of this is a positive root k. So I'm going to need a root k up in the top for each one of these, right? So I need a root k here. I need a root k here. That puts a 1 over root k out in front. And that means I can put this out here. That allows me to integrate these. And so what I get is the len of this minus the len of this. All right, now what we might notice here is m over root m. Those can cancel, leaving a root m up top. So what we have here is 1/2 m over gk rooted. And inside here, these can be combined into one natural log. All right, let's get rid of this coefficient by moving it over to the right. We're going to multiply both sides by 2 over the square root of gk over m. Again, multiplying by 2 over the square root of gk over m. This will still be a constant over here, so we'll just write that as a plus c. And let's go ahead and figure out what that constant is. Remember the initial condition? Velocity at time 0 is 0. So putting in 0 for the velocities, you get the natural log of root mg over root mg. That's the natural log of 1, which becomes 0. Here, t is 0, and so c is 0. So that term is really just 0. Okay? That makes life a little bit easier for us. Now we can get rid of the natural log, exponentiate both sides. E to the 2 gk over m rooted times t. Now think about how you're going to go about solving this for v. Right? You're going to multiply both sides by this denominator. Let's get you onto a new page here. We got plenty of scratch paper. Might as well use it. Multiplying both sides by root mg minus root k times v, we get the numerator here equals this times the denominator. And then this times this. Now this term has a v, and this term has a v. Let's put those together. That's going to be k, root k, plus, and I'm going to go ahead and factor the v out, so I'll take root k, e to the 2 root gk over mt, all times v, equals on the right-hand side, I'm going to have this term minus this term that I bring over. Okay? So, finally, to get v by itself, I have to divide by this. All of this divided by this. And there's your solution. All right, now recall what we really cared about from this, perhaps in our simple example, was what happens as time goes on. What terminal velocity do we achieve? Well, as t goes to infinity, what you're going to be left with is this as the dominating term in the top, and this is the dominating term in the bottom, meaning this term and this term are going to become insubstantial. Okay? Inconsequential, I should say, as t goes to infinity. Okay? And so v approaches this. Root mg e to the 2 gk over m times t over root k e to the 2 gk over mt. And guess what? These cancel. And there's your terminal velocity. Okay? Now, compare that to the other two cases. Again, in the first case, there was no terminal velocity. That's where we said there's no such thing as air resistance, right? So the object just keeps falling faster, faster, faster forever, velocity going to infinity. In the second case, we said let's model air resistance as proportional to your velocity. So if your velocity doubles, your air resistance doubles as the object falls. And what we got for the terminal velocity was mg over k in that case. That was right here in the case 2. The terminal velocity was mg over k. Finally, we do this realistic modeling where we say that the velocity squared is what contributes to the air resistance, not the velocity. And we get a terminal velocity that's very different of that. It's the square root of that mg of k over k instead. Okay? And so this is the type of modeling one can do when one wants to model any falling object. For example, a skydiver is something we're very familiar with because most of us are familiar with the concept of a terminal velocity for that skydiver, that they're going to reach some final speed as they fall, right, due to air resistance. Well, this is why it's occurring, and this allows you to actually understand that final speed. Okay? This could also be used in understanding or modeling how other objects fall, like droplets. When somebody coughs, how long does a droplet stay in the air? Okay, the different modeling procedures can give you very different results. If somebody does a linear modeling of the resistance to the particle as it falls, they get mg over k. If somebody does a quadratic model, they get root mg over k. And these make big differences sometimes in how long you might say that a droplet is in the air. Okay? All right, so that's it for this special example. I hope you found it somewhat interesting. I certainly did. I like this type of a problem quite a bit as to show the power of how differential equations can be used in modeling real-world processes. So hopefully you had fun with that. I know it's kind of an arduous task to slog through these things, but think about what you get in the end in terms of a true understanding of how this object is falling. Okay? That's quite a sophisticated thing to be able to do. It's well worth the effort. Certainly much more valuable to your understanding of something than working those arbitrary exercises you do as you go through the section in preparation for an exam. Okay? All right. If you have any questions, don't hesitate to contact me. and I'll look forward to talking with you.